Up to this point, we have looked at examples that exclusively use the sensible heat equation or latent heat equation. But as you might have guessed, in the real world, many situations involve both sensible and latent heat. Let's try an example.
So we have 5 pounds of 100-degree water. So that water is below its boiling point by 112 degrees, since we know the boiling point of water is 212 degrees Fahrenheit. And we want to find out how many BTUs are required to change that water into 212-degree steam. So we're going to break this problem into its two components. First, the sensible component. We'll apply the sensible heat equation, which is Q equals mc delta T. Right? And we have everything we need to know to solve this problem. We know the mass is 5 pounds. The specific heat of water is 1 BTU per pound degree Fahrenheit. And the delta T is the difference between our 212 degree final temperature and our 100 degrees that we're starting at. So that's 112 degrees Fahrenheit. So let's plug those numbers in. 5 pounds times 1 BTU per pound degree Fahrenheit times 112 degrees Fahrenheit. And then we can just get out our trusty calculator. 5 times 112 is 560 BTUs. Now it's important that we don't get lost in these problems and think, oh, we arrived at our solution. No, this is just a component of our solution. We've now raised the temperature. This thermometer now reads 212 degrees Fahrenheit, but it's still water. So now the question is, how many BTUs are required to cause the water to change from 212 degree water into 212 degree steam? And of course, we're going to apply our latent heat equation to that. So a little squiggly line, our latent heat equation is Q equals our mass times the latent heat of vaporization. For water, the latent heat of vaporization is 970 BTUs per pound. So plug both of our numbers in. Q equals 5 pounds, 970 BTUs per pound. And just plugging that in the calculator, 5 times 970 equals 4,850. BTUs. Again, we still don't have a final answer. The final answer will be the sum of our latent heat and our sensible heat. So the total heat, Q, and I'll just put a Q with a little t, equals 560 plus 4850. Both of these are BTUs. And when we add that together, the answer is 5,410 BTUs. That would be the BTUs, or the heat required to raise the temperature of our water to 212 and then boil all of the water. I want to point out something here, that the sensible component is approximately 10% of that answer. Not exactly, but approximately 10%. And it turns out in most of these combination problems, the latent heat will dominate in terms of the overall. You still can't ignore the sensible heat because 10% is still 10%, but most of the time the latent heat will dominate. All right, in this example, this is kind of the most complicated example we'll have to interact with in this course. We have 2 pounds of water that's in the steam form, and it's at 220 degrees Fahrenheit, and we want to change it all the way into ice at 10 degrees Fahrenheit. All right, so at first glance, this might seem intimidating, but don't be intimidated, because each individual step, we have all the tools to complete. There's actually 5 steps to this problem. The first step, we need to cool our steam from 220 degrees Fahrenheit down to the boiling point of water, which is 212 degrees Fahrenheit. Since we have a temperature change, that's a sensible heat problem, cooling our steam from 220 down to 212 degrees Fahrenheit. Once we're at 212 degrees Fahrenheit, our next component is latent heat. We need to change our steam into water at its boiling point, no change in temperature. The third component will be back to sensible heat. We're going to change our water from 212 degrees down to 32 degrees Fahrenheit, which is the freezing point for water. And then we again have a latent heat component. That's component number 4, where we're going to transition our water into ice. Still 2 pounds the whole way through. Then our final component will be sensible heat once again, where we lower the temperature for ice from 32 degrees Fahrenheit down to 10 degrees Fahrenheit, where we get to our final state that the problem asks for. So let's go one at a time. We'll do component 1 first. Okay, so since we're dealing, I'll just put a 1 here so we know we're dealing with the first component. Okay, since we know we're dealing with a change in temperature, we will apply our sensible heat equation. Q equals mc delta T. We're dealing with steam here, and so it's important to recognize that the specific heat of steam is 0.5. It's half of the specific heat of water, so that's important to know. Once we know that, though, we can just plug in everything else. We have 2 pounds of this steam, 0.5 BTUs per pound degree Fahrenheit, and our temperature change is 8 degrees. We got to go from 220 to 212 degrees. So that's going to be an 8 degree Fahrenheit change. Get my calculator here, although we could probably do it in our head because 2 times a half is 1. 1 times 8 is 8. So Q equals 8 BTUs. All right. Step 1 of 5 complete. I'll go ahead and underline that to keep track of it. Now let's move on to step 2. This is the latent heat required to change our steam into water at 212 degrees Fahrenheit. So we'll apply the latent heat equation. Q equals mH. Okay, our mass is still 2 pounds. It'll be 2 pounds the whole way. And the latent heat of vaporization of water is 970 BTUs per pound. So 2 times 970 equals 1,940 BTUs. Step 2 complete. Notice the difference. Again, latent heat nearly always dominates over the sensible heat. Okay, move to step 3. Okay, step 3, we now have water that's at 212, and we need to cool that water down to 32 degrees Fahrenheit. So substantial temperature change. All right, we're going to apply the sensible heat equation. Q equals mc delta T. Because we're dealing with water now, our specific heat will not be 0.5, it'll be 1 BTU per pound degree Fahrenheit. So I gotta make sure you apply the right specific heat. We have 2 pounds of water, 1 BTU per pound degree Fahrenheit. And our temperature change is 212 minus 32, or 180 degrees Fahrenheit. Okay? 180 degrees Fahrenheit. So pretty substantial change in temperature. All right. So our answer here, plugging this in, will be 2 times 1 times 180, which is 360 BTUs. Notice quite a bit more sensible heat changing the temperature of our water as compared to changing the temperature of our steam in component number 1, which was only 8 BTUs, but still quite a bit less than the latent heat required to change our steam into water. All right, moving forward, step 4. Now we have our water cool all the way down to 32 degrees, and we need to make it into ice. All right, so that's a perfect use of our latent heat equation. Q equals mH. Now in this case, our M is still 2 pounds. That's the easy part. And now H, it's not 970 because we're not going between water and steam. Instead, it's 144 BTUs per pound, which is the latent heat of fusion for water. Okay, 2 times 144, that equals 288. BTUs. Step 4, complete. So we've completed steps 1 through 4. On to our final step. We're sitting on 32 degree ice, and we need to cool that ice down to 10 degrees. So we need to cool it 22 degrees. That's our delta T. So let's do our final calculation. Q equals mH. C delta T. Once again, we're not dealing with water anymore, so our specific heat of ice is also 0.5 BTUs per pound degree Fahrenheit. It's the same value as it is for steam. So let's plug in our numbers. We have about 2 pounds, 0.5 BTU per pound degree Fahrenheit. And we're going to multiply that times 22 degrees because we need to get down to 10 degrees Fahrenheit from 32. Kind of do this even in our head because 2 times a half is 1. 1 times 22 is 22. So we have 22 BTUs. Okay, we have completed all of the steps required. So the final thing we need to do is simply add up step 1, 2, 3, 4, and 5. So I'll do that on the calculator here. We have 8 plus 1,940 plus 360 plus 288 plus 22. And our final answer, I'll write it right here, total amount of heat that must be removed is 2,618 BTUs. That is our final answer. That many BTUs would need to be removed from 220 degree steam in order to make it in a 10 degree ice. So the final thing I want to point out about this before we end this session is that the 1,940 BTUs required to change it from steam into water really dominates. In fact, 1,940 divided by the total, which is 2,618, is 74%. So almost 3/4 of all the heat removed was done in our transition from steam into water, which is very significant and an important concept to understand when learning about refrigeration.